Hello, everyone. What I want to do is finish up monotone sequences, section 3.3 in the book. So in particular, remember we had the following example that we didn't finish. So we had x1 was 3 and xn plus 1 is 1 plus square root of xn minus 1. Okay. So last time we proved that this was decreasing. Okay. And we didn't just guess this, we discovered it by calculator, basically writing out the first couple of terms, and got lucky and we noticed that it's decreasing, or we noticed that it should be decreasing, and we proved that. Okay, so let's get a lower bound. Well, one fairly obvious lower bound, technically you should prove this by induction, but you're always taking, so, by really easy induction, xn is always going to be bigger or equal to 1. So, yeah, so because xn is always going to be, basically by an easy induction, xn is always bigger or equal to 1. That's a lower bound, but we're going to get a better lower bound that's going to be useful for us to figure out what the limit is. Okay, so I claim, and this is still pretty easy to prove, that 2 is a better lower bound. So xn is bigger or equal to 2 for all n natural. Okay. So this is absolutely trivial. For n equals 1, x1 is 3. 3 is bigger or equal to 2. Okay, so not that it matters, but actually let's do a little better. Let's do bigger than 2. Okay. So still true. X1 is 3 is bigger than 2. Okay, so let's assume xn is bigger than 2. All right, and let's just write inductively what this is. So xn, xn, that whole thing, minus 1. Make sure we have that. Yeah. All right, so this is bigger than 1 plus square root of 2 minus 1, because xn is bigger than 2. Well, this is equal to 1. 1 plus 1 is 2. So by induction, it's true for n, it's true for n plus 1. Okay, so let's see how this helps us. So this accomplishes, well, first and foremost, 2 is a lower bound for xn, so it's decreasing, bounded from below. So by the monotone convergence theorem, it has a limit. Okay. So let's say x is the following limit. Okay. So we know that any m tail of this converges to x, and in particular, we're going to look at the 1 tail. Okay. So this means x is going to be this limit. Okay. And what is this? Xn plus 1, the definition is 1 plus xn minus 1 square root. And by the limit laws, this is 1 plus square root of x minus 1. Okay. So what do we have here? Let's see, 1 second. There's this colors here. Yes. X equals 1 plus square root of x minus 1. That's what we have proved. Okay. How does that help us? Let's see. So x is 1 plus square root of x minus 1. X minus 1 is square root of x minus 1. Square both sides. X squared minus 2x plus 1. That's going to be x plus 1 squared. Now square this. Gets rid of the square root. It's 1. X squared minus 3x minus 2 is 0. So we have two possibilities. X minus 2, x minus 1 is 0. Okay. Now, if I had in-person class, I would ask, well, x can only be 1 or 2. Which one is it? We know which one it is. Okay. Why? So xn is bigger than 2 for all n. So by the limit laws with respect to inequalities, as we did an example, it does not mean the limit is bigger than 2. It means it's bigger or equal to 2. Okay? So x is bigger or equal to 2. Okay? So x is either 2 or either 1. Well, that's not really true. X can't be 1 because x has to be bigger or equal to 2. And 2 is bigger or equal to 2. 1 is not bigger or equal to 2. 1 is smaller than 2. 2 is bigger or equal to 2. Okay. So, yeah, so cross that out. So that means x equals 2. Okay, so let me do one last example. So I would actually do e as an example as a limit of 1 plus 1 over n to the n. It's actually a nice little example using the binomial theorem to prove that 1 plus 1 over n to the n is increasing as n goes to infinity, or just increasing. It's bounded above by, I think, 3. Yeah. Well, you can look at that in the book. There's really not enough time to go through that. But anyway, so I do want to do one. I think it's a kind of neat example. This is actually an example that goes back to, I think the book says, the Babylonians. It's a very practical algorithm to compute square root of any positive number. Okay. So yeah, this is also from the book, but I think this is worthwhile. So this is going to be a little different than the prior examples we've done. I'll explain why in a second. So let's say S1 is anything positive. A lot of times when you have an algorithm that works for any initial kind of point here, or any initial elements, you want to pick this judiciously so that your algorithm runs fast. We're not going to get into that. But yeah, so let's say S1 is positive. And let's say Sn plus 1 is 1/2 Sn plus A over Sn. Okay, so as I said, this is an algorithm to compute square root of A, where A is positive. Okay. So just a note here. I guess it's not even, I don't know if it's even worthy of proving, but I guess. So S1 is positive. So I claim that Sn for any n is also positive. Okay, well, it's true for one. It's kind of trivial, but so if Sn is positive, A is positive, so Sn plus 1. Well, I'm just adding two positive numbers times a half. Everything is positive here. So, okay. All right, so I can do a lot better than that. A lot better lower bound. So I claim that actually Sn is bigger or equal to square root of A for all natural numbers. It's a very clever little argument to do this. I probably would not have thought about it myself in a million years, but right. So let's say X is Sn. So usually X is the limit of something. Here, X is not the limit. There's a reason why I'm going to use X in a moment. So Sn plus 1 is 1/2. I'll erase stuff in a second. This is just a definition. This is a definition. But I'm saying let's call this X. Let's call Sn X. So it's X plus A over X times 1/2. Okay. All right, so let me multiply by 2x. So 2x Sn plus 1 is equal to, well, 1/2 x times 2x is x squared. 1/2 a over 1/2. Sorry, a over 2x. A over 2x is going to be times 2x is going to be equal to sorry about that. A little interruption here. I'm in my house, the house I grew up in. Yeah, sorry. So this is going to be just A. Okay. So I'm multiplying A over 2x by 2x, and it's just going to be A. Okay, sorry about that. So what that means is, sorry. So let's write this out as x squared, just subtract 2x Sn plus 1. Sorry, it's plus A. Okay. So this Sn, which we called x, satisfies the equation x squared minus 2x Sn plus 1 plus A equals 0. And it might look a little neater if I put the 2 Sn plus 1 in front. Okay. So what does this mean? Okay. This means that, well, I have a quadratic that has a real root. The coefficients here are 1. The other coefficient is minus 2 Sn plus 1. And the third coefficient is A. Okay. And so you take the... so that means when you do the quadratic formula, you don't have any complex roots. Okay. And remember, it's square root of b squared minus 4ac. So this is it's kind of like my a, my b, and this is sort of like my c. So that means that when I take square root of kind of b squared minus 4ac. So let me just, maybe if I'm not being clear here. So let me do this here. Oops, didn't mean to do that. Okay, so this is sort of like my a for my quadratic equation. This here, I guess, minus this is minus 2Sn plus 1. I don't really need parentheses here. Okay, so remember the quadratic formula. It's x is plus or minus b squared. Not really that important. So that's going to be, sorry, swear I remember the quadratic formula. Negative b. So minus b is going to be 2Sn plus 1 plus or minus the square root of b squared. Now this is what's important. Minus 4ac. B squared minus 4ac. So it's 4a over 2a, just 2. Okay. Now I know Sn is, it's positive. Sn is positive. Sn is a real number. Okay. So the only way we get that this is a real number is if this thing inside here is bigger or equal to 0. If it is negative, we have complex solutions. So this has to be bigger or equal to 0. Okay. Sorry. It is b squared. Squared. Okay. So what's b squared? Well, it's really 4Sn plus 1 squared. So 4Sn plus 1 squared is bigger or equal to 4a. So Sn plus 1 squared is bigger or equal to a. Same thing as Sn plus 1 is bigger or equal to square root of a. As for all natural numbers, sorry, this is for all natural numbers. So maybe quite true. So this is true for all integers n bigger or equal to 2. This is true for all integers bigger or equal to 2. Because this is true for all integers, this is true for all natural numbers. And so we have n plus 1 here, where n is any natural number, and that means that's the same thing as saying Sn is bigger or equal to square root of a for all n bigger or equal to 2. Okay. All right, so let's put that to good use. Okay. So I now claim that basically this sequence is decreasing. So Sn plus 2 is less than or equal to Sn plus 1 for all natural numbers n. Okay. So I would say in general, when you have a sequence defined inductively and you want to prove it's monotone, try induction first. In this case, you will realize that it's tricky. And you can probably do it, but I'm not sure how to do it. So try something else. And what's another reasonable way to prove this? Well, we can just, this is enough, it's enough to prove that obviously, this is equivalent to Sn plus 1 minus Sn plus 2 is bigger than or equal to 0. And so this is just another strategy. If induction doesn't work for these kind of inductively defined sequences, this is just another strategy to try. Because you can get Sn plus 2 in terms of Sn plus 1, and maybe this will work. I would still first try induction. Usually that works, not always. All right, well, what's this? Just plug in a definition. So it's Sn plus A over Sn. Okay. Sorry, plus 1. So it's Sn plus 1 plus A over Sn plus 1. Okay. So we could simplify this. We have Sn plus 1 minus 1/2 Sn plus 1, which is just 1/2 Sn plus 1. And then we have minus 1/2 A over Sn plus 1. Let's get a common denominator and pull out a 1/2. So it's Sn plus 1 squared minus A over Sn plus 1. This first term here is just 1/2 Sn plus 1 distributed. The second half term here is 1/2 minus 1/2 A over Sn plus 1. Yeah, sorry, I have my dog right next to me here, so that's why I'm sticking my arm out. I'm petting her right now, make sure she doesn't interrupt this Zoom lecture. All right, so what on earth is the point here? Well, we know this is bigger or equal to 0. Why? Because we proved that just a minute ago that Sn plus 1 is bigger or equal to A for all natural numbers n. Okay. So we proved that Sn plus 1 squared is bigger or equal to A for all natural numbers n. So Sn plus 1 squared minus A is bigger or equal to 0. The denominator is always bigger or equal to 0. It's bigger than 0. We proved that, so no problem there. So yeah, this is bigger or equal to 0. Okay. So what have we proved? In other words, this is saying the one tail, X here. That's my dog right there. So the S tail is decreasing. That's what we exactly just proved. Okay. All right, so yeah, we can now figure out what this limit is using the limit laws. Pretty straightforward. Okay, so the one tail is bounded below by square root of A. It is decreasing, so it has a limit, and it's equivalent to just the sequence itself having a limit. Okay. So Yeah, so let's figure out what that is. Call it yeah, I'll call it still x, not to be confused with calling Sn x here, but yeah, it's fine. So let's say x is this limit. I'll use the same kind of logic as before. Let me call it s. I'll call it s. No reason not to. Okay. So it's the one tail. The limit s is s is also the limit of the one tail as we did last time. So this is 1/2 Sn plus a over Sn. And this is going to be 1/2 s plus a over s. So what do we have here? We have s is 1/2 s plus a over s. Right? S is certainly bigger than 0. Okay? Because, well, s, so remember Sn is bigger or equal to square root of a. A is positive. That's our assumption here. So limit laws are fine. S is bigger than 0. Each Sn is bigger than 0, so no problem. All right, so S is 1/2 S plus A over S. So what does that mean? Subtract 1/2 S from both sides. S over 2. Is A over 2S. Okay, so multiply both sides by 2. S is A over S. We'll multiply both sides by S squared. So by S, we got S squared is A. So again, as I said before, the whole point is this gives me a concrete algorithm to compute the square root of A. Okay. You can program this into a whatever you want. I don't know how fast this algorithm is, but yeah, I do not know how fast this algorithm is. But yeah, you can easily program this into any programming language, do it like a for loop or whatever. I guess not for loop, but you just define this inductively, like this way, and this will give you a way to compute the square root of any positive. All right, so next we're going to talk about subsequences, and I'll divide that up into 2 videos, one on just subsequences and another one on lim-sup and lim-inf, because lim-sup and lim-inf are very important and I want to spend a little bit of time on it. So, all right, sorry for all the interruptions. Hopefully this was good, and I'll see everyone on Wednesday. Take care. Goodbye.